Hi guys. So what we're going to do now is we're going to work through some sample exercises for chapter 5.2 so that you can see how the formula is used in practice. The first example we're going to do is the example I sort of hinted at the end of the lecture. So you have to be careful with the way that the wording of these problems is phrased because they indicate the area that's going to be usually revolved around some axis. The axis of rotation is going to matter in these questions. So this question says, find the volume of the surface obtained by rotating the region bounded by the x-axis. Y is equal to x squared. X is equal to 0. And x is equal to 1 about the x-axis. So that's a lot of information to be contained in a setup for a problem. And this is part of why I'm so adamant that you guys draw pictures when you're getting ready to solve one of these questions. If you can't visualize the region that you're looking at, it's going to be very difficult to figure out what the surface of revolution turns out to be. So I'm going to draw the region that we're going to do the revolution of first. So let's see. We're bounded by the x-axis, by y equals x squared, by x equals 0, and x equals 1. That means that the region that we're looking at is the part of the parabola y equals x squared that's underneath the curve and above the x-axis and bounded on the left-hand side by 0 and bounded on the right-hand side by 1. And so the region that we're looking at is this region in here. So the idea is that we're going to take that region and we're going to rotate it around the x-axis. So I'm going to do this on the next slide so I have more room. Okay, so example 1 continued. So the region that we were dealing with looked like this. And it was this inside here. And then what it wanted us to do was to take that region and we're going to take this area and we're going to rotate it around the x-axis. So that's going to give us an idea of what the shape should look like. So the middle of spinning this thing around is going to be the x-axis. So the shape you're going to get out the other side is going to look something like sort of a curved horn like this. Where if you wanted to draw the original shape inside, that original region would look something like this inside here. Okay. So hopefully you can see the relationship. Now, if I want to find the volume of this object, I'm going to have to come up with a representational cylinder or representative cylinder that I can use to compute the volume of, and then I can add up the representative cylinders to find the volume of the whole thing. So that is, I want to take this object and I want to cut all the way down. So, a representative slice. So the representative slice for this looks like, well, if I took this and I sliced it, I end up with looking like a little cylinder again. So I'm going to expand this so that it looks like this. Where this piece right here, this is R, that's the radius, and the radius goes from the axis of rotation up to the function. Because remember, up here is some function f of x. So this is f of x. That point right there is on f of x, and the center of the rotation is here on the x-axis. I know the volume of this cylinder already. Remember, this is a cylinder. So I know that the volume of this thing should be the base area times the height. The height is easy because we're chopping things in the x direction. So the height here should be the base area times delta x. So what is the area of the base? Well, it's going to be a circle with radius given by the distance from here at the x-axis to here on the function. That is, I'm looking at this right here, right? This radius right here, and it shifts as we go down, but it's always dictated by where I am on the x-axis. So I'm going to assert that the base area of this thing, b, is equal to, well, the distance from the axis to the function, that's just x squared. That's the radius. And then we square that and multiply by pi. That's the base area. Okay, so what do I do with all this stuff? So here's our region. And here's our shape. And here's our representative slice. Which ended up expanding into something that looked like this. It has a circular base, so I know that the base area B is equal to pi r squared h. The r was the radius from the x-axis up to the function. It's skinny in the x direction, so I know the height of this particular cylinder is delta x. This radius right here is equal to x squared. That's the radius because we go from 0 up to the function. And so the volume of this thing is equal to pi x squared squared delta x. If I want the volume of the entire shape then, so the volume of this thing, the entire shape, is going to be, well, where does the slicing begin? We start at 0 because that's where it told us the region began, and we finish at 1 because that's where it told us the region ended. Then we're going to use the integral to add up the volumes of all these little cylinders, so we get pi times x squared squared, not delta x anymore because we've taken a limit and we're in an integral, so dx. And I want you to really be able to look at one of these integrals and recognize that all of the pieces are the geometric things that we identified when we drew these pictures. This part right here, this is b, a base area of a circle. And this is little h, the height of some cylinder. At this point, all you have to do is take the integral that we've written down and solve it. Okay, so if we want to do this, where this curve is given by y is equal to x squared, and this is x equals 0, and this is x is equal to 1, then the volume is equal to the integral from 0 to 1 of pi x squared squared dx, which is the integral from 0 to 1 of pi x to the 4th dx, which is 1/5 pi x to the 5th, evaluated from 0 to 1, which is just 1/5 pi. Okay, so it could be the case that these objects are spun around a different axis besides the x-axis. And this is part of why I don't want you to memorize formulas if you can avoid it. I'd prefer that you derive the formula from the situation that you're looking at. So let's look at a problem where instead of rotating around the x-axis, I'm going to rotate around the y-axis instead. Okay, so this time what I'm going to do is I'm going to look at a region that looks like this. I want to look at the region y is equal to x squared, but now instead of rotating it this way, I'm going to rotate it this way. So I'm going to take this region, and I want this region to be bounded, say, by, so this point is 0, 0, and this point is the point 2, 4, and I'm going to take this region and I'm going to spin it this way. So I take this region and spin it around the y-axis. So that the object we're going to get out this time is going to look like this, which is called a paraboloid if you're interested. Okay, so we could try to look at formulas and figure out, okay, is it a dx integral, is it a dy integral? But it's actually easier just to write down what a representative slice looks like and then derive the formula from the slice. So in this problem, what we're going to do is we're going to pick out slices that look like this. And I know that my axis of rotation for this shape, where it cuts through the parabola right here, that's the y-axis. And that means that if you tell me what y value I'm located at, so where is this slice located, it's located at some height y. So y is some height on the y-axis where this slice is located. If you told me y, I could tell you the radius, because all I have to do is get from the axis of rotation out to the function, right? So this thing right here is going to be the radius this time. It'll be clearer once I actually draw the slice. So what does the slice look like by itself? It looks like this. Now, what are the dimensions of this slice? Well, it was skinny in the y direction, right? So this time we're dealing with a thing that it's got little tiny increment in y thick. So it's very thin, but it's thin in the y direction. And so what that means is the height here is delta y. This is delta y tall. Now I also need a radius. I know that the radius starts here at the middle, which is the y-axis, and it runs out here to the function. Now the problem with using the function y is equal to x squared is that I'm supposed to be giving you a y value and you tell me an x value. The way that y equals x squared is set up is you give me an x value and I tell you a y. So what I'm saying here is if I have y is equal to x squared, that takes x values and spits out y values. But I don't need to know y values. If I'm looking at this function, I need to know where the x value is here. I need to know how far I went in the x direction. So I can't use this function. I have to change it, not as a function of y as a function of x, but x as a function of y. You give me a y, I tell you the x. So I'm going to invert this by solving for x and get x is equal to the square root of y. This is a function that if you tell me the y, I can give you the x. So this function defines the radius from 0 in the middle out to x is equal to the square root of y on the outside. And the reason that it's a function of y is because all of this is dependent on where this slice was located, which is a y value. Okay? So how do we put all this together? So that's the setup for the region. If we actually do the rotation, we end up with this paraboloid with that typical slice. The volume of that typical slice is going to turn out to be, let's see, it was delta y tall, and the radius r was equal to root y. And so the volume of this typical slice, v, is equal to root y squared, so pi r squared h. Pi r squared h. Where do the slices begin and end? Well, in this problem, the region had y values. Remember, I'm slicing in the y direction, so I need to know which y values I can put these slices at. Well, what were the points we were dealing with originally? We started at 0, 0, and the curve went up here to 2, 4. What are the y values involved? Well, from 0 to 4. Those are the possible places where the y slices could be located. So we're going to write an integral down telling us where the location of the slices could actually be. So the volume of this shape v is equal to, well, it starts at y equals 0 and finishes at y equals 4. And the base area of each of these little cylinders was equal to pi times root y squared. And multiplying by the height to get the volume of the cylinder, we have dy. So this is just the integral from 0 to 4 of pi y dy. And the last thing we need to do is just to do the integral. So the volume is equal to the integral from 0 to 4 of pi root y squared dy, which is the integral from 0 to 4 of pi y dy. which is equal to pi over 2 y squared evaluated from 0 to 4, which is pi over 2 times 16, which is 8 pi. Now, if you want to be pedantic, it's actually 8 pi units cubed, but that's not going to be a factor in the way that we're starting to think about these problems. Because units are sort of a dimensionless quantity in abstract calculus, I'm not going to include them. When we start working on physics problems, the units will actually mean quite a bit. So in those contexts, we will include them. Okay, so the next video will cover more complicated examples. Work hard.